The first thing is the jet.
Give it another minute for some people to trickle in and we'll get started. All right, I think that's a good number of people to get started. Good morning, everyone. Thanks for joining us today. My name is Phil. I'm in the sales department with Odell. And today we're going to be discussing some industrial retrofit solutions with Cambridge Air. We'll be discussing some of the benefits of HTHV technology and kind of how we can overcome some challenges when it comes to retrofitting some of these older facilities. Dave Binns is with us today. And Dave is a VP of engineering over at Cambridge, and he's going to be conducting the rest of this presentation. If there are any questions, please feel free to drop them in the chat. And at the end of the presentation, we'll have a quick Q&A. There will also be a certificate of attendance for anyone here that will come from Anna Maria within the next week or so. Yeah, so without further ado, let's take it away, Dave.
Thanks. Thanks again, everybody. Thanks for joining me today, and I'm grateful to have this hour with you to talk a little about just some of these challenges with industrial buildings, and talk a little about some of the ways that we've addressed some of these issues and how we can help you help your customers create healthier environments. So again, thanks again. Like I said, my name is Dave Binns, VP of Engineering for Cambridge Air Solutions, manufacturer here based in Chesterfield, Missouri, just out of St. Louis. For those that maybe are not familiar with Cambridge or what we do, we say that we help leaders in manufacturing warehouse create healthier working environments for hardworking people. We do that through the products that we manufacture, also just the ways that we engage with our end users, our engineers, our contractors, and even other manufacturers to help create healthier working environments through lean manufacturing and kind of people-centric cultures. When we talk about Cambridge, again, if you're not familiar, one of the things that, just to give you an insight to what we do, more than just manufacture equipment, our customers say that they like using Cambridge because they provide support for life and make industrial HVAC the easiest solution. We manufacture products that are the most energy efficient for their application. We build equipment that's built to last and try to last as long as these industrial facilities, sometimes 20, 30 years. We build everything to order, but still have some of the shortest lead times in the industry in a highly variable, customized solution environment. And then our team of experts that first start with our local representation partners like Odell and our internal application engineering team and other engineering team. We want to help you solve these complex problems where really off-the-shelf products and solutions don't typically meet the needs in these types of applications. So we won't talk a lot about products, but we'll talk more about applications today. But just some of the different solution sets that we provide at Cambridge. Most people know of us for some of our commercial industrial space heating products. We also manufacture and provide industrial ventilation and makeup air products through some of our other M-Series applications. And as we've been primarily in the heating ventilation space for over 60 years, many of the end users' challenges in built environment expectations are changing where they want more temperature relief and more cooling in these facilities. So in the last 10 years, we've been adding a lot more capabilities around temperature relief with some unique evaporative cooling technologies and also other unique ways to provide industrial air conditioning when we actually do want to provide a temperature controlled space conditioning technology. So we've got a wide variety of solutions and products, all geared towards large warehouse and manufacturing. But today on the application side, we're going to talk focusedly more on industrial retrofits. So what do we mean by industrial retrofits? Really, retrofit is in any large open space where I've got an existing facility and structure, and then now my building operations, my design conditions, or really my built environment is starting to change. So we don't have the benefit of a blank slate, clean sheet like we do in new construction. And we've got, and sometimes these retrofits can be buildings as old as, say, this is maybe a year into a tenant retrofit, or we're dealing with a 80-year-old manufacturing environment that's been built and modified and added onto over the course of many decades, where the interior looks nothing like it did day one. And that provides some really unique challenges when we start talking about solving for HVAC challenges. So the biggest challenge that we see about these industrial retrofits, really first and foremost, is how do we work around this existing infrastructure with evolving operations requirements, right? So we've got an existing building, existing structure, whether that's the building, the roof, the structural steel. I've got pieces inside the building that are moving around, operations, manufacturing equipment, racks are moving in this highly variable indoor environment, and the structure that exists and is very difficult to retrofit. How do I provide new solutions that is going to interact with this built environment? That can become a big challenge when we're trying to do this, and also work inside of an ongoing operations where there may be active manufacturing or industrial working in the facility. And secondly, I think, more so in like our bread and butter, which is, I think, a challenge that many of our design engineers and contractors deal with on a daily basis, but particularly when we look in industrial retrofits, how do I balance these ventilation needs and indoor environment quality needs with energy consumption? Typically in our design projects, we're balancing this seem to be trade-off of increased ventilation, increased indoor air quality with a increase in operating costs. And in a manufacturing environment where trying to balance those, and sometimes with a cost structure where increasing operating costs can be detrimental to a manufacturing environment that may have very slim margins, it can be a difficult challenge to work inside those capital constraints and energy constraints while trying to provide a more comfortable and safe environment. So let's talk about the kind of the again, I mentioned the type of industrial retrofits, existing buildings. I'm also going to break those down and segment those into kind of two different segments, because there are some key application differences that impact the way that we design an HVAC system for those applications. And I'm going to break those into what I would consider your warehouse distribution and your manufacturing industrial. So there's a lot of similarities and there's some unique differences. Most of these buildings are large, open, high bay facilities. We've got big open spaces. Sometimes we're 100,000, 500,000, maybe even 1 million square feet facility. We say high bay because typically the floor to roof decking is anywhere from 26 to 40 feet, sometimes even taller. And those present some unique temperature distribution challenges that we'll talk about a little more in depth. Uniquely, both warehouse and distribution and manufacturing, they want to minimize first costs and minimize operating costs, right? Both these types of buildings and operations are trying to balance, investments in their HVAC over investments in their operations. And that can often be a tricky scenario when we're trying to recommend HVAC solutions. But when it comes down to the HVAC system, one of the biggest differences between these two facility types is how we are dealing with ventilation, the ventilation challenges. In the warehouse distribution, most of the ventilation is driven by your ASHE 62.1 or your minimum ventilation requirements, which can be fairly low for a large open space. There's also some infiltration that we'll talk about a little bit later. But in the manufacturing industrial, now this ventilation can be extremely high. If I have a very dense, process intense manufacturing environment, I may have very high requirements for ventilation and makeup air driven by process exhaust, ovens, other types of heat capture or indoor contaminants captures, which can be highly variable based on process. So I may have big open spaces on one side, maybe little amount of outside air requirements, and the other side, high amount of outside air requirements. That varies tremendously from unoccupied to occupied, or even from shift to shift. So with that, the building's the same, the structure's the same. Most of these buildings may actually have the exact same construction, walls, insulation, and type. However, now when I look at the HVAC system, I got to look and solve my ventilation first. And so in the warehouse, I'm typically driving my heating ventilation solutions on primarily a heat-driven requirements because I have low ventilation requirements. And then the manufacturing side, now it's the opposite. I have low heating requirements because of maybe internal heat gain or other types of challenges. But now this highly variable ventilation requirement pushes me into more of a ventilation-driven solution. And so we're going to talk today about those differences, how it impacts our HVAC solutions that we might recommend, or how we might actually combine some of these two, as many of these facilities have almost a combination of both spaces, maybe even in the same facility. So let's talk about manufacturing and industrial first. And we're going to focus on that building type, primarily because whether it's warehouse and manufacturing, we want to make sure we're solving the ventilation problem first. So when you think about industrial buildings, one of the challenges that we see very often is you got an existing manufacturing operation, and many manufacturing leaders, they're very production and operations focused. So they're making changes to their operations, they're adding production, they're adding welding, they're adding process, which creates indoor contaminants that start to change the indoor environment. And oftentimes HVAC experts and engineers don't come in until after an indoor air quality problem has already existed. So you got a building, they added process, they add indoor contaminants. What's the first thing we do? Well, we got to solve the indoor air quality problem. Let's add some exhaust fans. So they add exhaust fans. We're capturing, containing all that exhaust fans. However, they didn't look at how it's going to impact the indoor environment from a temperature perspective. So a building that was cool and comfort and 65 degrees, now I've added a lot of exhaust. It's negative building, negative pressure. I've got all this untreated, untempered infiltration coming in, and our temperatures are dropping. And so that's often when we get involved on the solutions. And how do we solve those ventilation problems? With a makeup air solution, right? We want to make sure we're actually providing that ventilation through a tempered, filtered makeup air solution. So we're going to bring that 100 outside air. We're going to filter it. We're going to temper it. We're going to heat it. We're going to deliver it to the space. So now we're going to be solving that negative pressure and that what seems to be a heating problem with ventilation. So we're going to provide temperature ventilation. We're going to provide that more ambient level temperature into the space. And so I may not be necessarily heating the space, but I'm actually tempering the ventilation. And so now what seemed to be a heating problem was actually a ventilation problem. And so that's really where tempered makeup air comes into play. So the technology solution that we show there in these industrial retrofits is in tempered ventilation through makeup air units. And in these large industrial spaces where I have high volumes of CFM, we're talking 50,000, 100,000, maybe even 500,000 of total CFM required to meet my pressurization because of the process. I want a solution that's going to be cost-effective first cost and cost-effective on an operating cost. And that's really where direct-fired makeup air shines. So direct-fired, in a sense, is I'm combining the ventilation with my gas directly and heating that through natural gas. It's a 92% thermal efficient combustion process. It's a 100% combustion efficient process where 92% is sensible heat, 8% essentially is latent heat or humidification, and with no flue losses and 100% and a fully variable combustion cycle, I can really make sure I'm matching my ventilation needs and my heating needs with no flue losses. So highly energy efficient, and we can process large amounts of air in a very simple solution set. So that's why many industrial manufacturers prefer direct-fired makeup air in these applications, because it's a simple and reasonable first cost and operating cost and maintenance cost system with minimal working moving parts no large heat exchangers to deal with, no flues in a simple stainless steel direct fired burner. So you mentioned earlier the challenges with industrial manufacturing is this ventilation load may be highly variable. This application could go from 100,000 CFM of exhaust to 400,000 CFM of exhaust as lines turn on and off, or as the indoor operations change hour to hour. And so this is where airflow and variable volume makeup air applications become highly advantageous. And we've been doing variable volume direct fired makeup air for over 25 years. We were some of the pioneers of actually being able to turn down airflow and modulate direct fired heat in a very low airflow and low heat application. So we've been doing this for a long time. But what that allows us to do is we want to match my ventilation load to my exhaust load. So I'm not over pressurizing the space. I'm not adding more air to the building than it would naturally breathe, which could cause building pressure problems, process problems, product quality problems, or excess energy. So look at how you can modify your airflow control. What we most often do is implement some VFDs into our airflow and our fans. We're going to be making sure that we can modulate that airflow based on either building pressure, maybe some other types of process signals. That's just trying to balance my airflow from exhaust and makeup air. And so now that I'm varying my airflow, I need to also make sure that I'm varying my heating source and varying my gas flow. So all of our direct fired, all of our heating applications, actually, whether it's makeup air or space heating, which we'll talk about later, is all a continuously variable, fully modulating heating controls. Now, fully modulating heating controls could also mean two different types of modulating heat control options. So two types of control that we see often in these industrial retrofits is either I'm doing discharge temperature control or I'm doing space temperature control. Sometimes in these large makeup air applications, I just want my makeup air to deliver neutral, filtered, neutral air. So I'm constant discharge, but as my outdoor ambient changes and fluctuates, I need to actually still be able to modulate my gas flow, modulate my heat to maintain a constant discharge. And that's where our discharge temperature control solutions are typically delivered. Secondly, depending on your application, maybe this makeup air system is going to provide my ventilation and my space heating requirements. So now I actually want to modulate my discharge temperature maybe above neutral air. So I want to go above, say, my 65-degree indoor set point. But as the ambient conditions change, temperatures, infiltration, other things might change throughout the season. Now I actually want to be able to modulate my discharge temperature up and down to maintain a space temperature. Those are two different options, but ultimately it's all about what does the customer want? What's the indoor environment and problem I'm trying to solve? How do I want to vary my airflow and my temperature and my heating source to make sure we're providing that, again, seamless indoor air quality consistently across a highly variable operating environment. Back to the challenges, one of the first things we talked about was the challenge of existing infrastructure. Many times when we're brought into these industrial retrofits, manufacturer really does not want to change their building if necessary. They don't want to cut holes in walls. They don't want to cut holes in roof. They don't want to reinforce structure. And, doing structural steel modifications or analysis becomes highly expensive and sometimes can make the project cost prohibitive. And so we want to say, I always used to say, use what the building gives us. And so if we've got spaced outdoors, let's put the unit on pads and duct in. We're not really putting any load on the structure. A simple pad or stand outside can do minimal building modification changes. Maybe I need to install some units in the roof because I don't want to have large, extensive use of ductwork. We've got a variety of ways to apply those equipment, vertical, horizontal, rooftop, pad mounts, indoors or outdoors. Maybe some locations they want to put the unit indoors and just provide my hood outdoors. But you've got a lot of options, and every building and every end user may actually have different requirements that you need to work with. And secondly is air distribution. Even on the ventilation side, most manufacturers of industrial spaces, they want to keep that indoor space as free of equipment and ductwork as possible. They want to have this open sandbox inside the space, because they're moving lines, they're moving equipment, they're moving racks, and ductwork that is used to essentially help us get distribution becomes now a challenge for how they want to be able to modify their building for future product needs, future operation needs. So we try to minimize that ductwork where possible, and we want to provide that fresh air, that ventilation into the building without having to really move any equipment or racking around as possible. And depending on what the building needs, where that exhaust is, we have a variety of ways that you might want to deliver that air through higher velocity distribution, lower velocity types of plenums, but ultimately look at what the building is going to give you and how you want to distribute the air on a large volume perspective, just to make sure we're getting that ventilation in at the right space and not trying to have pockets of high temperatures or warm or cold spots. So again, a variety of systems in the industrial application, but get what the building give you, solve your ventilation problem first, and then provide some unique control options, modulation options, or ductwork to make that overall system match their operations. That's a quick overview of the manufacturing industrial space. Now let's go into warehouse distribution. So from the outside, these buildings may look a lot alike, right? They're big, open, 100,000, 200,000, maybe 1,000,000 square foot big open boxes. But now, since I don't have a lot of that indoor heat generation, indoor process, maybe off-gassing of contaminants or high ventilation requirements, I'm actually going to deploy some different heating solutions. And so we're going to talk about that and how the warehouse distribution retrofit space is unique. And now I'm going to deploy different technologies. So when we look in high bay space for a warehouse, again, fairly similar to what you see in the manufacturing space. But now, since I don't have a high process exhaust requirements, the building changes a little bit. In the warehouse space, high bay spaces are very susceptible to stratification. As hot air rises, that heat that we want to get to the floor at the operators that are working at the floor, it can be a challenge. And without looking at different and how we deploy certain technologies, distribution, pressurization can cause an impact to your HVAC system. Also, constantly battling infiltration. So because I may have a low ventilation requirements, most warehouses and distribution and existing facilities have really inadequate ventilation to overcome infiltration. As buildings as it gets really cold in the ambient winters, I've got high winds coming across, I've got stack effect and stratification. Sometimes this infiltration become a very sore thorn in our side to making comfortable conditions. And many times when we look at industrial retrofitting warehouses, we've got lots of dock doors, perimeters that are very cold and drafty because of inadequate ventilation solutions. We'll talk a little more about that. And then finally, temperature distribution. As warehousing indoors and technologies change, we're seeing much more high density racking, high density storage. So how do you get good temperature distribution inside the space? And almost even more stringent than industrial manufacturing, where warehouses, they want to have as much product as possible inside. So now ductwork becomes the enemy, because any kind of ductwork or distribution strategies that somehow limit the ability for me to add racking or product becomes a challenge with warehousing business leaders. And so the often technology that we use in these large warehouses was what we call HTHV, or high temperature heating and ventilation. Similar to a makeup air unit in that it's 100% outside air. However, there's a few key differences to the system and the performance that allow us to do some really unique things from an overall built environment. And that's the high temperature, meaning greater than 140-degree temp rise and a greater than 150-degree discharge temperature. And then again, these fully modulating controls so that I can meet my ventilation needs and my space heating needs, again, with this modulating gas system, so that I can do both in a variable environment. So just to make sure that we're clear on the differences, because oftentimes we hear these used words synonymously: a makeup air heater, a makeup air unit. an industrial space heater, an HVAC unit. They seem to be used kind of synonymously, but there's some key differences. The makeup air draw systems are typically draw through, higher volume. Draw through meaning the blower is downstream of the burner. So my motor and my bearings and my fan is downstream of the hot airstream. Because of that, I'm typically limited to discharge temperature. I don't want to go higher than really 120 degrees because now my motors and bearings, their life expectancy and half-life is going to drop significantly. If you talk to any motor manufacturer, they'll tell you for every 10 degrees above 104 Fahrenheit, they lose about a half-life. So you start looking at 135-degree discharge temperatures in these makeup air units that I see sometimes from other manufacturers. Those motors are getting burnt out every 5 years. Still no heat exchange, no flue losses. But when we talk about HTHB, we do one simple thing where we move the blower upstream of the burner. We put the blower in the cold airstream. So now I'm pushing or blowing that air through the burner. And now my motor and bearings are in the cold airstream. And so with that, I can actually increase my discharge temperature so I can get more heat in a lower volume. I get more heat into a smaller box. And so I can do more space heating where maybe my ventilation requirements are a little bit lower, which is what we often see in warehouse spaces. And so, but just first and foremost, whether it was manufacturing, we know that we need to use outside air and solve my ventilation problems. Many times we get into warehousing and retrofits, and they want to actually minimize all outdoor air because they think outdoor air is going to increase my energy costs. But like we said, and we know as design engineers in the HVAC world, every building needs outside air that's going to be designed for human occupancy. And that outside air requirement may be a low requirement for mechanical ventilation or some variable infiltration. And when I add those two together, that becomes essentially my air load. And so when I'm talking about energy efficiency, even we said whether it's warehousing, industrial, or manufacturing, let's solve the ventilation problem first. And so if we take a warehouse, so maybe this building might be a 300,000 square foot facility, and they still have maybe a lower, or let's say it's 150,000 square foot facility, lower outdoor air requirements. They may only need around 10,000 CFM to meet their ventilation requirements. That's not a lot of air. That's not a lot of ventilation in a big open space. And if I want to be able to heat that and provide that ventilation energy efficiently, I'm going to use, again, a direct fired system, no heat exchange, no flue losses. There's your makeup air system. But what does HTHB do? Well, now instead of adding other types of space heating, other recirculation space heating systems like package rooftops, unit heaters, any other type of maybe a gas-fired or heat exchanger style heating source that has flue losses, if I can just use my ventilation system and increase my discharge temperature, I can get a lot more heat to heat other losses, whether that's skin losses or maybe even some additional variable infiltration losses. So now, in essence, this is what HTHB does. It takes that 10,000 CFM makeup air unit, turns it into a 10,000 CFM industrial space heater and ventilation unit that can do my ventilation needs and have over 1.1 million BTUs of usable heat for skin losses, conduction losses, or a variable infiltration around perimeter and my dock doors. So that's kind of, like I say, the core of the heating side of the HHB. But how about the system side? In industrial retrofits, where I said we're trying to balance indoor air quality, balance temperature distribution with energy costs, the biggest driver for energy challenges in warehousing is stratification. I want that heat to the floor. And if the heat rises due to the low density of hot air, in many applications, we've seen 15, maybe even 20 degrees of temperature distribution stratification, where it's, say I'm controlling at 65 degrees the floor. Well, it could be 85 degrees of the ceiling. And that can create now a lot of excess energy. Now my mixed air temperature is almost 75 degrees. I'm heating that building to 10 degrees warmer than it needs to be. And that stratification induces more infiltration. So now my infiltration rate could potentially double because my stratification is so poor. So a variety of ways to deal with destratification. HVLS fans, high velocity fans have become a commonly used solution in existing facilities to deal with just the destratification challenge. However, if I'm trying to solve a ventilation, a heating problem, and a destratification problem, what our HTHB solutions can do is actually induce air distribution. It can pull that kind of stagnant warm air at the ceiling down to the floor, utilizing high velocity. So dealing with providing high distribution, so high velocity temperature at a 45-degree angle towards the floor, we can induce about 10 CFM for every 1 CFM of air that's processed by my mechanical fan. So take that 10,000 CFM, 2 million BTU HVAC system. By the time I deliver that heat to the space, I actually have roughly 100,000 CFM of air movement in the space by utilizing that induction principle with high velocity. So these can be used in conjunction with HVLS fans, or in many cases, they can be used in the absence of HVLS fans. So when we think about HTHV, when I'm retrofitting an existing warehouse space, my single unit can provide the same effects of 6 high-efficiency unit heaters, distribution technology like HVLS, and also some tempered ventilation needs to meet my ventilation, my distribution, the dehumidification, and my space heating needs. And now in one package where I'm trying to minimize equipment in the space, minimize distribution, and lower my install costs with lowering my operating costs, we have a really unique package for that type. This technology is a really unique package for that. When we talk about design considerations, these systems can be zoned, and every building is going to be different. Even every warehouse may be different. The same 2 warehouses next to each other could have completely variable use. One building could have like 10 dock doors that are used all the time and 90 that never do. The other building could have those 100 dock doors open all the time. And so how we utilize that building usage, the nice thing about industrial retrofits is we at least know what's going on in the building. Sometimes in new construction, you're designing for future expansion, future use. You don't even know how the operators are going to work. But industrial retrofits, we kind of know a little bit where those maybe challenging spots are. And we can put these units and solutions in unique applications, configurations, and locations to make sure we're solving those temperature and ventilation needs. Similar to the makeup air applications, these solutions can be highly flexible for where and how you install them. Again, horizontal or vertical, outdoor or indoor, roof mounted, pad mounted, or even wall hung. One of the things we see often inside of these warehouses that typically you're going to put maybe the equipment on the roof, even a 2 million BTU space heater is still only going to weigh about 2,000 pounds and still be the size of maybe your traditional desk or credenza, not a very big piece of equipment. So it doesn't take up a lot of space. And so these equipment can be utilized and moved around the facility without having to do too much to the building structure again. In the warehousing space, we talk about, the challenges of existing facilities. More and more of these warehouses are built very, very thin with as minimal structural steel, tilt up construction and minimal roof structure and insulation. I've seen many existing warehouses that can barely handle some snow loads. And so now it's even more critical about how we're putting smaller equipment, lighter equipment, or where we're putting that equipment to make sure that the building can handle the HVAC systems without having to do major building modifications. So finally, let's go into some actual real-world examples. We're going to go into a few different projects that maybe had different indoor challenges, maybe different goals for the end user, and different ways to analyze what was provided and what the outcomes were. We'll start with a simple one, a simple warehouse retrofit. So this is a 500,000 square feet warehouse. The building was about 20 years old. It was installed previously with roughly 50 unit heaters. Your kind of traditional indirect fired, 80% efficient unit heaters. The building had no real mechanical ventilation. So with that, they had high stratification. They had very uneven temperatures from floor to ceiling and wall to wall. The building had really no pressurization, no mechanical ventilation. And so as you can imagine, dock areas were very cold and drafty as those dock doors open and that infiltration came in untempered, untreated. The building could have been 65 degrees in the middle of space, but they are feeling that, harsh 0 degree, negative 10 degree air coming in that dock door. And so very uncomfortable conditions for their workers. Afterwards, they wanted to balance improving their ventilation, trying to get a better pressurization of the facility, and ultimately trying to reduce the energy cost And so they installed 6 HDHV industrial space heaters and ventilation. They were able to actually meet current ventilation codes and provide much more even temperatures. Now, since I was really trying to offset that infiltration with my HDHV, I didn't have those very cold, drafty, negative pressure problems at the dock areas. And my high velocity systems allowed me to greatly de-stratify the space. So what you're seeing here is actually kind of a before and after of temperature loggers throughout the facility. So on the left, this was your before with many unit heaters. The black bar is the ambient temperatures outdoors, and the multicolored are various temperature sensors throughout the facility, floor to ceiling, wall to wall. And so you may see in some cases where we get to, roughly 5 degrees ambient here, we were seeing, 55 degrees at one area and almost 68 degrees in another area. So we have, 10 to maybe even 12 degrees of variation in stratification, which is causing a lot of energy losses. Afterwards, even when it got down to below freezing, we saw below freezing in 2 different conditions, and our temperature band is much, much, much tighter. We're anywhere between 62 and 65 degrees, wall to wall. So really good temp distribution, even in more harsher outdoor ambience. And we actually improved ventilation. So this building had no mechanical ventilation. They added mechanical ventilation and still saw over 30% of their total energy costs being reduced, and even at a higher indoor temperature. So really a great example of how your traditional HHP industrial space heaters can improve indoor air quality and reduce energy costs in a traditional warehouse retrofit facility. So this is an interesting topic that's become up a lot more here in the last 4 or 5 years. It's kind of balancing decarbonization and electrification, even in a retrofit facility. So maybe we had the example of a building where, yes, they were concerned about reducing their energy costs, but they're also concerned about reducing their carbon footprint. Existing facility, improve indoor air quality, improve temperature control, and reduce their greenhouse gas emissions. And this facility, at first, looked at electrification as a solution set for lowering their total carbon footprints, as opposed to just overall energy costs, right? So decarbonization, electrification can actually mean 2 different things. So let's look at this example. So this is actually a 1 million square foot warehouse located in the state of Washington, Spokane. They were really providing minimal heat. It was just a large distribution center, roughly only 40 degrees inside the space, so not a very high indoor heating load. It got close to 0 degrees outdoors. To meet your indoor air requirements, it only needed 120,000 CFM of mechanical ventilation. So over 1 million square feet, that's a fairly small amount of outside air. And the total heat load was around 12 million BTUs, or 3.5 thousand kW. So if you think about that, that's my total heat loss, regardless of what technology I put in there, across my ventilation needs and my skin losses or my conduction losses. And what we did with this customer, who actually was originally looking at utilizing electric heating and electrification technologies to solve their greenhouse gas emissions. And so what we did was, let's actually analyze how we would utilize high efficiency gas heating versus high efficiency electric heating and their actual greenhouse gas source emissions. This is really the kind of, I would say, hidden factor when looking at electrification or decarbonization challenges is, where am I getting my power from and how clean is my power? So believe it or not, the northwest of the US and many parts of Canada have actually pretty clean power with a lot of hydro. However, there still are some pockets of natural gas or coal. And so on average, the national average, at least in the US, is around 800 pounds per megawatt. In Spokane, they were below that national average at about 600 pounds. So pretty clean power. However, here's what natural gas, when we look at space heating, we have a very low CO2 emission, only about 400 pounds per megawatt. So, about half of the national average. And we were about 2/3 of what it would look like inside of this facility. So again, the goal for this customer was improve ventilation, improve thermal comfort, and reduce greenhouse gases. And what we did is we analyzed that if I use natural gas versus utilizing electric heat, what actually is the CO2 emissions? And so by utilizing their, again, this was using electric resistance heat. I know there are some applications where heat pumps could be an alternate solution. However, in this application, there really is no heat-only heat pump solution that was available to them. This was heating only, and where we needed that heat at 0 degrees. And so they were utilizing electric resistance, which is then has a COP of 1 across the full operating range. Gas heating has a COP of 0.92 and a much lower emission rate. So if you think about that, gas heating in a direct fired environment on a kind of, I would say, heat to heat basis is about 38% less carbon output than the electric resistance heat. So this building, when they compared the usage of gas fired heat versus electrification, again, with the goal of decarbonizing, they were actually going to increase the building's total carbon emissions as we look at from a source energy perspective, which is what their goal was. And so they were able to analyze that even in an industrial retrofit where carbon emissions is my driver, sometimes natural gas or gas-fired heating systems may actually be the best solution to lower my carbon footprint. Again, every building is going to be different. But so not only was that the carbon emissions applications, but also total cost of energy. You know, electric heat can be extremely expensive with some electric resistance heat applications. And in this case, you know, they weren't even looking at operating costs at first. It was primarily being driven by greenhouse gas emissions, but we were able to save that end user, you know, almost from doubling their energy bills inside their HVAC system. So all in all, when we talk about electrification, we want to make sure we're balancing operating costs, greenhouse gas emissions, and ultimately the source emission rates for my power. Secondly, well, I'll also add that this is obviously a hot topic these days, is just the available power usage, but many buildings do not have enough power to electrify, and retrofitting existing buildings is a prime example. If I look at existing warehouses, existing manufacturing spaces, you know, their electrical requirements, their total power available is very limited because operations in manufacturing gets the first, I would say, pull at whatever available capacity they have. You know, in this building, which is just warehouse, they're going to have to add, you know, 3 2,000 amp panels just to electrify the building. And the cost of that was going to be astronomical. And really, the local utility didn't have the available power to give to them. And especially now as data center construction has just exploded in the last 5 years, all of our grids are being stressed. And so when we think about electrifying buildings, we've got a long way to go to building our infrastructure before every building is ready to be turned over to electrification. But many advancements coming out through heat pump technology and other types of space heating technology. We're also working on a few of those. But as we look at, you know, what are the solutions available today with our business leaders' challenges today to solve their problems of today, but set up for tomorrow, we want to look and see what different solutions that we might want to look at. Let's talk about a traditional manufacturing environment. So this is a high output welding facility. So industrial, lots of robotics, still a lot of people, but with all of this process, all this welding facility, we've got a lot of indoor air quality challenges and ventilation challenges that change throughout the life of this facility. In actuality, this building started out as a roughly simple warehouse distribution facility, but they brought operations and they brought production to the building. So same building, same infrastructure. This building was actually built with HTHV fully functional to provide the space, heating, and ventilation for a warehouse. But now that I'm adding so much welding, now that I'm adding so much process, we know that we have to do something to make sure we're still controlling our indoor air quality. And so they added exhaust fans. That was the first thing they did. They knew they had some welding. They knew they had hoods. They knew they had exhaust to make sure indoor air quality. Great. Installed it. Guess what happens next? They forgot to think about makeup air. They forgot to think about how that was going to impact the building's pressurization. And so now this facility became very negative overnight. And what happened was, you know, the operations, the production team said, "Hey, I've got a heating problem. This building was you know, nice and warm. I added all this process, and now it's freezing. What do? I need more heat. Give me some unit heaters. Give me some space heaters." Well, you know, as design professionals, we want to stop and take and look at the whole building, look at the operations, and realize you actually have a negative pressure problem. You've got a ventilation problem. You don't have adequate ventilation for all this process you've added. And now this facility happened to do it all at once. most buildings, you see them added kind of like one at a time. I had one exhaust fan here, one exhaust fan here, one exhaust fan here. And slowly over time, that temperature becomes colder and colder. My negative pressure gets worse and worse. But this was all at once. And so instead of adding just straight heating, we didn't want to add a lot of Band-Aids to these symptoms throughout the perimeter of the building. We want to actually make sure we've got an adequate ventilation strategy. So we added some dedicated variable volume makeup air systems. These automated process lines had variable ventilation needs. And so adding a large amount of makeup air, we want to make sure that that makeup air solution could match my exhaust rate. And so a variable volume building pressurization strategy, in addition to the existing HVAC systems, created an environment that now allowed them to really match building operations with ventilation, keep my indoor environment pressurized and temperature controlled and filtered in a, again, highly variable indoor environment. So as we look at maybe larger industrial retrofits where I've got, a variety of spaces of maybe some storage, maybe some light manufacturing, maybe some heavy manufacturing, ventilation that's going to change throughout the day, shifts that I may be one shift this week, I may be 3 shifts next week, a variety of solutions. And in this case, a combination of HTHP and makeup air were used to handle, a varying conduction load, varying infiltration rate, and a varying ventilation rate to meet their needs. Very, very common that we see in industrial facilities. So I'm going to give you one more example, and then we'll open up the floor to some questions. But this is, I think, definitely a unique challenge that we're seeing more often in many manufacturing spaces is I've got my heat solved, I've got my ventilation solved, but man, this seems like my process is getting hotter, my building's getting hotter, the ambient's getting hotter, and my employees are getting more and more uncomfortable, unsafe, and I need to provide a system that allows them to knock the edge off in the summer. And so in this facility, this was a welding, manufacturing, and assembly facility. And what they had was a process on the north end of the building that had a variable welding, paint, and curing process that it would get extremely hot in the north end of the building. But pretty much wintertime, great. Shoulder months, great. But man, the summer, it just got unbearable. And it was very difficult to keep employees safe and even retain inside that north end of the building. And so what we did is that we looked at, how can we still make sure we're meeting your ventilation needs, but providing some temperature relief. I may not, if I deployed a traditional comfort control or mechanical cooling, my energy costs would be outrageous because I've got a 400-degree oven, I've got 40,000 CFM of a process exhaust. That's extremely expensive to add a lot of mechanical cooling. But what we deployed here was actually utilizing 2-stage temperature relief with 2-stage evaporative. So evaporative technology can be extremely energy efficient, and in many high internal heat gain applications, by delivering neutral air, when I say neutral, maybe even space temperature neutral, like 75-degree air in a 110-degree environment, can actually provide enough temperature relief without using a lot of energy. 2-stage evaporative cooling can actually get your discharged air temperature below the ambient wet bulb with utilizing a fraction of the energy that you would with mechanical cooling. It's not going to dehumidify, it's not going to fully condition, but it could take, in this case, what was over 90 degrees facility, bring it down to about 77 right at that production line with adding no mechanical cooling whatsoever, and also meeting their process needs. So we talked a lot about a variety of problems, buildings, and challenges. Really, when we think about industrial retrofits, the first thing I always say is really solve your ventilation problem first. Where's my ventilation problem? Where's my exhaust? How am I handling my ventilation needs first? Then start to look at deploying other technologies. We want to limit infrastructure modifications. Manufacturing operations, they want to be able to get in and out as fast as possible. They do not want to disrupt their ongoing operations. And so that's how some of these technology can be deployed without really modifying the building. Improve indoor air quality while reducing energy. We saw a couple examples of how we can do that in these existing facilities. But ultimately, every building is going to be different. Every region is going to be different. Every challenge may be different. And looking at a variety of solution sets, technologies to meet highly variable loads and built environments can be critical when we're looking at industrial retrofits. So with that, that's all the content I got. And I'm going to open up to the floor for questions. We got any questions in the chat?
Nothing yet. Let's give everyone a few minutes here and then see what comes through.
Thanks, Phil. Well, feel free to come off mute, raise your hand, or even add a question in the chat, and happy to answer any questions about the content today, or even other questions about Cambridge Air Solutions or these technologies. We got a
hand up here.
Go ahead. I think, Phil, you have to take, is it Abraham off mute?
Yep. You should be off mute.
Still can't hear you, Abraham.
We have a question from Sohail in the chat. For hot and humid environments like Florida, do you provide mechanical cooling with your units?
Yeah, great question. We do provide some mechanical cooling options, whether it's, and we have a variety of mechanical cooling. I think in, say, a hot and humid environment like Florida, if we're talking about industrial retrofits, again, we'll look at the ventilation problem first. You know, sometimes I want to actually provide somewhat of a tempered and maybe dehumidified air. And so we can provide, you know, DX cooling, chill water cooling, matching with a variety of mechanical cooling options. You know, Cambridge, we wouldn't provide the actual chillers or condensing units, but we can match any type of DX or chill water application. Interestingly, we've had a massive increase in demand of that mechanical cooling on large makeup air applications. And so we can do that through both DX cooling or chill water cooling. Interestingly, if we talk about buildings where maybe I don't have a large mechanical ventilation challenge, now we can actually start, and this is what we're seeing more and more inside of warehouses. You know, really about 5 years ago, Amazon started cooling their new construction facilities because they saw productivity increases, employee retention increases, and then now more and more warehouse distribution can't get away with just, you know, your 3 air change of summertime ventilation relief. And we've actually just started to release a unique industrial cooling application for large warehouse and light manufacturing, where we're doing some mechanical cooling or chill water cooling with, again, high velocity systems to get distribution without having a lot of ductwork. So happy to talk about more that. So if you got an application down in Florida, we got a variety of solution sets for you.
Next question comes from Abraham, and do you have a heat recovery option?
Yeah, great question. We can do some heat recovery in a few different solution sets. So, and again, it'll be dependent on warehouse versus manufacturing. We'll start with manufacturing. When I'm doing the manufacturing industrial ventilation, most often my ventilation is being driven by an exhaust that has a class of air that is unacceptable to utilize in most traditional heat recovery. So we don't do many, you know, traditional enthalpy wheels or types of heat exchanger from energy recovery. We see a lot more, honestly, glycol loops, runaround loops, because that process exhaust air is so nasty that any chance of cross contamination is actually a highly risky ventilation strategy. So when we see heat recovery on the industrial ventilation side, it's a lot more of maybe like a glycol loop, runaround loop from an energy recovery perspective. Interestingly, in the warehouse side, one of the things that we do, we actually don't provide heat recovery on our high temperature HCHV units because when I'm looking at, so maybe now my exhaust might be available for energy recovery because my exhaust is essentially exfiltration. However, in warehouses, when I'm doing an HVAC solution, my exfiltration now is going out through 1,000 cracks and crevices along the dock doors, and potentially even millions cracks and crevices around the building. So even with HHV, my building may be slightly neutral to slightly negative. And what we've seen is that buildings that have tried to add heat recovery by adding an exhaust with, say, even a 75% energy recovery efficiency, I still have 25% energy, available energy that I couldn't recover. And when I add that exhaust to the building, we've actually seen buildings where they increase their energy usage by deploying heat recovery. So it kind of depends on the building, how they're using it. But I would say we can deploy some energy recovery where we have lots of mechanical exhaust and industrial mechanical exhaust, but how we're going to do it may be different than the way that you do heat recovery in, say, traditional office space or a makeup air application for an office, a school, or a type of application. And then the warehouse energy recovery sometimes can be difficult to actually quantify the energy savings unless you've got a really, 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 really tight building. And most large warehouses I see, particularly in the retrofit space, are extremely leaky. And so adding exhaust to make energy recovery actually increases their energy usage.
Awesome. Yep. And next question comes from Dave. And how often do you employ the evaporative cooling solution?
Yeah, great question. Interestingly, I would say these days what I see in our ventilation temperature relief, it's about 50-50. So I think, when we have customers that are looking at adding tempering to their ventilation strategy, half the time they're going to be using some evaporative cooling, but more and more people are looking at utilizing mechanical cooling. I think, evaporative cooling can provide really good benefits, even in I would say regions that aren't your traditional dry climates. And so, your direct evaporative is not going to work in a more moderate temperate climate. It'll work fantastic in a dry climate. And we see a lot of use of the direct evaporative there. But even when we get into those away from those dry climates, again, it depends on what the process is. If I have a lot of internal heat gain and I've got a building that has 50,000 CFM of ventilation need and it is 110 degrees inside that facility, adding mechanical cooling can be very cost prohibitive. So that's where we see a balance of, and that's really where indirect evaporative cooling in two-stage, which is a unique way of evaporative technology that most, I would say, contractors and users, engineers don't often see every day. It's used a lot in some data center markets, the indirect evaporative cooling, not as much in the industrial manufacturing. And so it can be really a unique way to provide cooling and ventilation where I'm not trying to completely dehumidify and comfort control the space, but I want to take a 110-degree indoor environment to 9 degrees without adding compressors. It becomes a very attractive solution.
All right, we have one more question in the Q&A section. It's from Ali. Can an evaporative cooling system reduce the indoor temperature in an industrial building below 77 degrees Fahrenheit? If so, under what outdoor temperature and humidity conditions? Also, what is the approximate install cost per square foot of the building area for a retrofit application?
Oh, great question. Yeah, I think so the unique thing, one of the challenges about evaporative cooling is that your capacity and your discharge air temperature is going to be really dictated by the ambient conditions, right? And I would say, in most direct evaporative, we talk about evaporative effectiveness as your ability to deliver discharge temperatures. And so evaporative effectiveness is out of, just like energy recovery, right? Out of the available difference between dry bulb and wet bulb, how much of that energy can I recover? How close can I get my dry bulb to my wet bulb? Direct evaporative is going to be about 90%. So if I've got a 20-degree dry bulb with wet bulb depression, I can get an 18-degree dry bulb depression in my discharge temperature, but my wet bulb is going to stay constant, right? It's an adiabatic constant enthalpy. So, if you have an application where I'm consistently seeing 70 to 72 degree wet bulb, I can easily deliver 74 to 75 degree discharge temperatures. And oftentimes, we see in an industrial facility where, it's 97 degrees regardless of wet bulb, right? Whether it's cold or hot. And so when my wet bulb drops, my discharge temperature drops. I would say in most conditions, direct evaporative cannot maintain 77 degrees unless you happen to be in, Southwest or in the a mountainous area where you have consistently low dew points and wet bulbs. The two-stage now, actually, because I do two-stage, which is sensible and then direct, or maybe even sensible and some mechanical cooling, so I can actually reduce some moisture, I can deliver air lower than my wet bulb. I can get 115% evaporative effectiveness. And so we've seen some applications where two-stage evaporative can actually achieve 77 degrees maintained. It all depends on what your ambient conditions are, your internal heat gain, and how that operations will look. But if you've got a client that wants to make sure I maintain my indoor environment below a temperature, and if you have any client that wants to control relative humidity, I wouldn't recommend only evaporative. That's where I'm going to want to supplement with some mechanical cooling because there may be conditions where I need a little bit of dehumidification. Install cost, difficult to say. I don't know if I can give you a rough a dollar amount there, but happy to talk about a project. We got a customer who you want to look at some budget numbers. We can throw stuff out for you.
Awesome. I think that's that wraps it up for the questions. So yeah, thank you very much, Dave, and thank you everyone for attending. And please be on the lookout for that certificate of attendance from Anna Maria in the next week or so. So thank you.
Thanks, everybody. Have a great day.
Take care. See ya. Bye-bye.